You know, it's funny. I feel like our brains just automatically default to the exact same mental image when we try to picture the beginning of everything.
Oh, absolutely. The classic void.
Right. You close your eyes and you just naturally imagine this vast, infinite, pitch black space, pure emptiness.
Just an empty room waiting for something to happen.
Exactly. And then right in the center of that dark void, there's this incredibly dense, impossibly bright little spark. And then, boom.
The big fireworks show.
Yeah. A massive explosion, cinematic fireworks blasting outward into the void, throwing shrapnel and light across the empty darkness, to eventually form stars and galaxies and, well, us.
It really is the ultimate opening shot of the ultimate movie.
Totally.
And it makes perfect sense why we visualize it exactly like that. We are incredibly visual creatures.
Right.
And we're used to watching things happen from the outside.
Yeah, from an external perspective.
Right. We naturally place ourselves in this hypothetical cosmic movie theater, sitting in the dark, watching the universe detonate on a blank screen right in front of us.
Right. But, and this is the crazy part, that image, that entire mental framework of the explosion in the void is just a complete fundamental illusion. It's totally wrong.
Completely wrong.
Because the Big Bang was not an explosion that happened inside space. It was an explosion of space.
Which is honestly the most crucial, foundational distinction we have to establish right out of the gate today for you listening. There was no empty void waiting to be filled.
No blank canvas.
No blank screen. There was no cosmic movie theater.
Yeah.
The theater, the screen, the dimensions of reality itself. That is what was expanding. Space itself was stretching.
Which is already hard enough to visualize.
It is. But even more difficult for the human brain to process, it was an expansion of time itself.
Yeah, and that right there immediately forces us to ask the most terrifying, just dizzying question in all of physics. If time itself started at the Big Bang,
the literal beginning of the clock.
Right. Then what in the world happened before it? So, welcome to today's deep dive. We are taking a massive stack of theoretical models, recent space observations, and brand new supercomputer research. And we're aiming it all directly at that single question: what came before the beginning?
And we should probably warn you right now, as you listen to this, you're probably going to experience a bit of vertigo today.
Oh, I've had vertigo all week prepping for this.
Because when you talk about time itself expanding from a single point, you run headfirst into a massive conceptual roadblock. If time did not exist prior to the Big Bang, then using the word before might just be entirely meaningless.
There's this brilliant analogy used by physicists to explain this, and it has literally haunted me all week.
The pole analogy.
Yes. It's the idea that asking what came before the Big Bang is fundamentally a category error. It's exactly like asking what is north of the North Pole.
It's honestly the perfect way to visualize the breakdown of our language and our logic here.
Right.
So imagine you're anywhere on Earth with a compass. You can travel north, you can walk, you can sail, you can fly, you can track your latitude all the way up the globe. The concept of north functions perfectly as a navigational tool.
Right, it makes sense.
But the absolute second you stand exactly on the geographical North Pole, that entire navigational framework just shatters.
Because everywhere you look is south.
Exactly.
The concept of north literally ceases to exist the moment you arrive at that point. There is no physical space north of the pole.
Precisely. The geographical framework has just reached its absolute structural limit. And time might operate the exact same way.
Man, that's wild.
If you rewind the clock of the universe, moving backward through the billions of years, the concept of before works perfectly. Yesterday, last year, a billion years ago.
Sure, causality holds up.
But the moment you hit the Big Bang, the concept of before just vanishes. The temporal framework reaches its limit. Time simply does not extend past that point.
Which, sets up the ultimate tension for everything we're going to talk about today. This central question is either a simple category error, like a linguistic trap we've caught ourselves in because human language requires a past tense.
Right.
Or it is the single most important unsolved mystery in the entire history of human knowledge. And the thrilling and kind of terrifying truth is that right now, neither we nor the greatest minds on the planet have any idea which it is.
We really don't. It's a mystery that requires us to examine the very limits of what science is even capable of achieving. So to really grasp the magnitude of this, we have to start by looking at why this question is so incredibly hard to answer.
The wall.
Yes. We need to talk about the breakdown of physics. We need to talk about the wall.
Because the crazy thing is, science is actually unbelievably good at rewinding the clock. I mean, we're not just blindly guessing about the history of the universe here.
Not at all.
When you read through the observational data, it is staggering how much we actually know about the early days.
It truly is. I mean, if you think of the universe's 14 billion year history as a film reel, we have almost the entire movie preserved in magnificent high-definition detail.
Yeah, we can observe the expansion of space, we can measure that background radiation, and we can mathematically rewind that expansion to describe the exact state of the universe at incredibly early stages.
We can go far, far closer than you might think. We can describe, with shocking, mathematically verified precision, the exact temperature, the exact density, and the specific behavior of fundamental forces just a microscopic fraction of a second after the expansion began.
Just a fraction of a second. That's insane.
Right. We can mathematically model the exact moment the cosmic fog of plasma cooled enough for the very first atoms to form, which allowed ancient light to finally travel freely through space. We can trace the movie back to the very first frame.
And here's the massive but. The moment we try to rewind that final microscopic fraction of a second, the moment we try to look at the absolute beginning, the singularity itself,
the physics we rely on completely shatters.
It just self-destructs. The math hits a brick wall. And we really need to dive into what hitting this wall actually means mechanically in the context of physics.
Because it's not just that we're missing a few variables in an equation. It's that the two foundational frameworks we use to understand reality actively turn on each other and just refuse to cooperate.
Okay, yeah, let's unpack that, because we have two incredibly successful maps of reality, but they map entirely different things. We have our map of the massive stuff and our map of the microscopic stuff.
Exactly. So on one hand, you have the foundational laws of gravity. This is our map of the macro universe. It describes how massive objects, planets, stars, galaxies, warp the smooth, continuous fabric of space-time.
Right.
Think of it like a beautiful, incredibly accurate topographical map of a sprawling city. It shows you the sweeping curves of the highways, the broad shapes of the neighborhoods. It's elegant, it's smooth, and it's predictable.
Okay, right. But then on the other hand, we have the laws of quantum mechanics. And quantum mechanics is the map of the incredibly tiny. It describes the chaotic, unpredictable, microscopic world of subatomic particles.
Very different world.
Super different. And unlike the smooth curves of gravity, the quantum world is jittery. It operates in discrete, chunky packets of energy. It is governed by probability and just fundamental uncertainty.
So, using our analogy, quantum mechanics is not a map of the city. It's a highly technical, hyper-detailed blueprint for the microscopic wiring inside a single microchip within one computer in one building in that city.
That's a great way to put it.
And both the city map and the microchip blueprint are perfectly accurate. They're both brilliantly useful for their specific purposes.
But if you try to use the sweeping city map to build a microscopic computer chip, you're going to fail completely. The scales are just fundamentally incompatible.
That is exactly the problem at the singularity. In our everyday universe, these two realms are neatly separated. Gravity handles the big stuff. Quantum mechanics handles the tiny stuff.
Everyone stays in their lane.
Right. But if you rewind the universe all the way back to the very beginning, you are taking all the mass and all the gravity of the entire cosmos, and you are compressing it down into a space infinitely smaller than a single atom.
So you're forcing the smooth, sweeping city map to perfectly overlap with the jittery, chaotic microchip blueprint.
And when you try to mathematically combine the smooth, continuous curves of gravity with the discrete, unpredictable chunkiness of quantum mechanics at an infinitely small scale, the equations literally self-destruct.
They just break.
The math spits out infinities. You get infinite density, infinite temperature, infinite curvature of space-time.
And as we know, nature absolutely hates infinities.
Infinities do not exist in the physical world. In physics, when a foundational equation spits out the concept of infinity, it is universally understood to be nature's way of saying your model is profoundly broken. Physics, as a descriptive tool, simply ceases to function at that barrier.
See, I find that wall absolutely fascinating. I really do. It feels like this ultimate physical boundary marker of human knowledge.
You like the mystery of it?
I do. It's like an ancient map where the cartographer just drew a line and wrote, "Here be dragons." It's the absolute edge of our cognitive reach.
I mean, I understand the romanticism of that. I really do.
Yeah.
But I have to push back strongly on that perspective because from a purely scientific standpoint, that wall is deeply, profoundly frustrating.
Frustrating. Why?
It is not some majestic boundary marker. It represents a glaring, fundamental failure in our understanding of reality.
A failure, just because we can't see past the beginning of time?
Yes, a failure, because the universe clearly knows how to combine gravity and quantum mechanics. The universe existed in that singular state. It happened. Reality knows the rules. The fact that our equations spontaneously combust at the most critical foundational moment on cosmic history means our rules are deeply incomplete. We are missing a massive, fundamental piece of the puzzle.
Okay, well, that is a totally fair point. The universe didn't break down, our math did, but it isn't like scientists are just throwing their hands up and walking away from the wall. People are actively trying to climb over it or just break right through it.
They are trying very hard, yes.
Which brings us to some genuinely wild recent research. As of June 2025, certain researchers have proposed a radically new way to try and push past this mathematical breakdown. And they aren't using chalkboards anymore. They're using massive, unprecedented supercomputer simulations.
Yeah, this is a highly experimental, deeply fascinating theoretical approach. If the math fundamentally shatters when human brains attempt to calculate it organically, these researchers are essentially proposing to use raw, brute force computational power.
Just throw processing power at it.
Right. They want to use computers to push our foundational equations of gravity and quantum behavior far beyond their known stable limits.
So basically, they're building a digital universe inside a machine, winding the clock backward and forcing the computer to handle the infinities that we just can't process.
Exactly. They are attempting to create digital theoretical environments that can sustain these extreme paradoxical conditions. The goal is to simulate the exact, jagged, smooth, infinitely dense environment of the singularity and see if the artificial intelligence or the sheer computational mass can extrapolate a pattern.
Wow.
They want to see what the physics might theoretically look like on the other side of the breakdown.
They want to digitally peek over the wall. They want the computer to tell us what happens when the city map and the microchip blueprint finally merge.
That is the hope.
Right.
Now, we must heavily caveat this. Of course, it is entirely theoretical. A simulation is only as good as the physics programmed into it.
Right. Garbage in, garbage out.
Exactly. If our core understanding is flawed, the simulation will just simulate those flaws at incredibly high speeds. But this research highlights just how desperate and ambitious the search for a new framework has actually become.
Yeah, it really does.
Because if our current math shatters at the edge of the Big Bang, we have to dream up entirely new conceptual models to explain what might be over that cliff.
Which is the perfect transition into the really mind-bending stuff. If the math breaks, what are these theorists dreaming up? Let's dive into the leading theoretical proposals for what happened before the universe began.
And these get weird.
Oh, they get so weird. And to you, listening to this, a quick heads up on how we're going to tackle this section. We are completely dropping the dense academic jargon.
Yes, please.
We are not going to use the formal, impenetrable names that get thrown around in university lecture halls. We're just going to look at the pure mechanical concepts themselves. Because when you strip away the jargon, the ideas are just staggering.
We challenge every single basic intuition we have about space, time, and existence.
Totally. So let's start with the first major concept. I like to visualize this one as the bubble in the foam. And the core idea here is incredibly humbling. It proposes that our entire universe, everything we've ever observed, the billions of light years of space, the trillions of galaxies, every star, every planet, is nothing more than a single expanding bubble situated inside a vastly larger, overarching, eternally expanding space.
The mechanics of this theory are absolutely fascinating to unpack. You have to imagine a background state of reality that is saturated with an incredibly high amount of repulsive energy.
Okay.
It's a space that is eternally, violently expanding outward. It never stops. It just stretches and stretches at speeds that defy comprehension.
But it isn't smooth, right? Like it has variations.
Exactly. Because of quantum fluctuations, tiny random changes in energy, this overarching space is not perfectly uniform. In random localized patches, that high energy state suddenly drops. It decays into a lower energy state.
It's like a pot of boiling water. You have this intense, turbulent, high energy liquid, but constantly little pockets of gas form. Bubbles pop into existence within the violent background.
That is a highly effective analogy. In this model, the overarching space is the boiling water, And occasionally, a localized patch drops in energy, the hyperrapid expansion in that specific area slows down dramatically, and a bubble forms.
And that bubble is a universe.
Right. The energy released by that drop condenses into matter, into radiation, into particles.
So, in this model, the Big Bang was not the absolute beginning of all reality. The Big Bang was simply the exact moment that our specific localized little bubble pinched off, dropped in energy, and began its own internal, slower expansion within the grander cosmic foam.
Precisely. And in this theoretical overarching space, this process never stops. Bubbles are constantly forming, constantly dropping out of the high-energy state. There are countless other bubbles, countless other universes constantly popping into existence forever.
I love this idea. I absolutely love it. It's so elegant. It completely solves the what came before problem by simply stating that there is an eternal background reality that has always existed.
It avoids the beginning entirely.
Yeah, there's no beginning to the overarching space. It just is.
Yeah.
And our universe is just one tiny, beautiful little snow globe floating in an infinite ocean of other snow globes. It makes us feel so small, but in a way that feels structurally sound.
Well, the mathematics behind it are incredibly elegant. It resolves a lot of issues we see in the early temperature of our own universe.
Yeah.
But here is where we have to put on our skeptical hats and ask the fatal question.
Oh, boy.
Can we ever, under any circumstances, actually test this?
Oh, come on. Why do you always have to burst the bubble? Pun fully intended.
I have to, because we are discussing physics, not science fiction. We require testability. Think about the physical mechanics of this model. This eternal overarching foam is expanding at an exponential rate. The space between the bubbles is stretching so fast that the bubbles are being driven apart faster than the speed of light.
Oh, meaning light from another bubble could never reach us.
Exactly. They are causally disconnected.
Yeah.
Nothing from the overarching space or from any other bubble universe can ever cross the boundary into our universe. We are fundamentally trapped inside our bubble with absolutely no physical way to look out, measure the foam, or interact with anything beyond our own borders.
So it's essentially a ghost theory. It solves the math, but it relies on a structure that we are permanently physically forbidden from ever seeing.
Which is the harsh reality of this model. If a theory inherently proposes a structure that we can never observe, measure, or interact with, we have to critically question whether it remains in the realm of hard science, or if it has crossed over into being a very elegant, mathematically consistent philosophy.
Okay, that is a devastatingly fair point. If we can't test the infinite space, let's pivot to a theory that tries to solve the problem by manipulating time instead. Let's look at the second major concept, the bouncing universe.
This is a profound shift in perspective. If the bubble theory says the universe is just one of many in space, the bouncing theory says our universe is just one of many in time. It completely discards the idea of a single, definitive beginning.
Right. Instead of a one-time explosion from a singular point, this model proposes an eternal cycle of recycling. The universe expands, it cools, galaxies form, stars burn out. But eventually, it runs out of that initial outward momentum.
It's entirely dependent on the mass and gravity of the universe. If there is enough matter, then eventually the collective gravitational pull of everything in the universe will act like a giant rubber band. It will overpower the outward expansion. The universe will stop stretching, and it will begin to contract.
An ultimate reversal. Galaxies start rushing toward each other instead of away. The background radiation heats up. Everything gets closer and denser and hotter until all the matter in the entire cosmos is pulled back together into an unimaginably dense, localized point. Big crunch.
And then, according to this model, the extreme, incomprehensible pressures of that total collapse trigger a rebound. It compresses to the absolute physical limit, and then it bounces violently outward again.
A new Big Bang.
Exactly. Expansion, contraction, crunch, bounce, repeating endlessly, forever, into both the past and the future.
It's like the universe is breathing, inhaling and exhaling over trillions and trillions of years. And what is deeply fascinating is that researchers are still actively modifying how this bounce mechanism might actually work.
Yes, there's been some very interesting recent work on this.
Right. According to recent literature, in October 2025, certain researchers proposed a brand new mathematical model that fundamentally rewrites the mechanics of the bounce.
Yeah, this was a significant theoretical development. For a very long time, cosmological models relied heavily on the idea of an incredibly rapid, hyper-fast expansion right after the beginning. They needed that rapid stretching to explain why the temperature of our universe looks so remarkably smooth and even in every direction we look today.
Like pulling a wrinkled bed sheet tight so it looks perfectly flat.
Exactly. But this new proposal from October 2025 suggests replacing that rapid early expansion entirely. They argue that a bouncing model doesn't need that sudden stretching mechanism because it can rely on something else, the extreme energy of gravitational waves left over from the collapse.
Okay, we need to explain how that actually works. Gravitational waves are basically ripples in the actual fabric of space, right? Like waves on a pond, but the water is space itself.
Yes. Massive cosmic events, black holes colliding, or in this case, the entire universe collapsing, create massive ripples in the fabric of reality. Now imagine the universe contracting toward the Big Crunch. As space gets smaller and smaller, those ripples, those gravitational waves, get violently compressed.
And when you compress a wave, its energy skyrockets.
Its amplitude and energy density increase exponentially. This new model proposes that as the universe crushes down to an almost infinitely small point, the concentrated energy of these swift gravitational waves becomes so intensely powerful that it actively begins to push back against gravity.
Wow.
The sheer geometric energy of the compressed ripples acts as a massive repulsive force. It acts as the cosmic trampoline that forces the universe to bounce back out.
That is mechanically brilliant. You don't need to invent some mysterious new repulsive energy field. You literally just use the kinetic energy of the ripples of the dying universe to fuel the explosion of the new one. It's a perfectly closed loop.
It is incredibly elegant. It creates a self-sustaining mechanical engine for reality. But we must return to our core problem. Testability.
I knew it! You're going to ruin the cosmic trampoline, aren't you?
I have to. Think about what a Big Crunch actually is. You are taking every star, every planet, every atom, every photon of light, and crushing it into a state of near infinite temperature and density. That process would completely annihilate all structure.
Right, it destroys everything.
It would destroy every single piece of information from the previous cycle.
It wipes the cosmic whiteboard completely clean.
Utterly clean. The extreme entropy of the crunch acts as an absolute firewall, which means if there were a previous universe, there is absolutely no surviving evidence of it for us to find. No fossilized light, no structural remnants.
It's rough.
So again, we are faced with a beautiful, logically sound mechanism that we have absolutely no way of proving.
Because the evidence of the past was melted down to build the present. Man, that wall at the beginning of time is thick. All right, if spatial bubbles and infinite recycling can't be tested, let's get into the truly bizarre stuff. Let's look at the third major concept, the quantum vacuum emergence.
This is where we fully leave classical physics behind and enter the deeply counterintuitive world of quantum mechanics. This is the proposal that the universe essentially tunneled into existence spontaneously out of pure, unadulterated nothingness.
And this is where we have to completely redefine a word we use every single day. We have to talk about what nothing actually means in a scientific context.
It doesn't mean what most people think it means.
Not at all. Because when I say nothing in normal life, I mean an empty box. I mean a room with the furniture taken out. Even in space, we think of nothing as a dark, empty vacuum where there just happen to be no planets or stars.
But in all of those examples, you still have a container. You still have space. You still have dimensions and time flowing forward and the laws of physics operating in the background. That is not nothing. That is just empty space.
So what is nothing?
In this concept, we are talking about absolute nothingness.
The total, terrifying absence of reality. No height, no width, no depth, no time ticking away, no rules of gravity, absolutely nothing.
Try to actually picture no space in your mind.
You literally can't do it. Your brain insists on visualizing a black void, but a black void is still a spatial dimension. Visualizing true nothingness physically breaks the human imagination.
It does. But while our visual imagination fails, quantum mechanics actually has a highly rigorous mathematical understanding of what nothingness implies. And this is the crux of the entire theory. Quantum mechanics dictates that a state of absolute, perfect nothingness is fundamentally unstable. It cannot permanently exist.
Okay, we need to break that down. Why is nothingness unstable?
It comes down to one of the most foundational rules of the quantum world, the Heisenberg uncertainty principle. Very simply put, this principle states that you can never perfectly simultaneously know both the energy of a system and the exact time of that system. There is always a baseline level of jitter, of uncertainty.
Okay, so you can't have absolute stillness.
Exactly. You cannot have a system sit at perfectly zero energy with absolutely zero change for infinite time. Nature outright forbids it.
So even if you have a totally empty void, it can't be perfectly still.
Right. Even in a pure vacuum, if you zoom in close enough, it's boiling, it's bubbling with microscopic quantum fluctuations. Virtual particles are constantly popping into existence out of the void, borrowing a tiny bit of energy, and then immediately annihilating each other and vanishing back into nothing a fraction of a second later. The void is alive with temporary microscopic energy.
So if you take that foundational rule that perfect stillness is impossible and that the void is constantly bubbling with temporary energy, and you apply it to the concept of the Big Bang,
You arrive at a staggering conclusion. If there was a state of true, absolute nothingness before the universe, that state was inherently, mathematically unstable. Its own rules of uncertainty dictated that eventually a fluctuation would occur.
but a big one.
Yes, instead of a microscopic virtual particle popping into existence and vanishing, it was a macro-scale fluctuation. A localized burst of extreme energy that tunneled out of the void and immediately began expanding.
The entire universe is just a massive runaway quantum glitch. Because absolute nothingness is so violently unstable, it literally had no choice but to birth the reality. It couldn't help itself.
It is an incredibly powerful idea.
Yeah.
The universe exists simply because nothingness is too unstable to remain nothing.
I find that deeply terrifying, but also utterly brilliant. But I know you well enough by now. I can see the logical trapdoor opening. Where does this theory fail?
The fatal flaw of the quantum emergence theory is a philosophical paradox wrapped in a mathematical assumption. We are saying that the universe popped out of nothingness because of the laws of quantum mechanics, specifically the uncertainty principle.
Right, because of the rules of the jitter.
But if there was absolutely no universe, no reality, no space, and no time, where exactly were the laws of quantum mechanics residing? How could a purely mathematical law govern a void that does not physically exist?
Oh, wow.
Exactly. It requires us to assume that the laws of physics are somehow transcendent, that they existed prior to reality itself, floating in some non-dimensional conceptual space, waiting to trigger a universe, which feels less like physics and more like theology.
If the rules exist before the game, who wrote the rules? That is a massive paradox. Which actually leads us perfectly into the fourth concept. And this one attempts to slice through all the paradoxes, all the bubbles, and all the quantum glitches with a single philosophical blade. Let's call this the meaningless question approach, or the no boundary proposal.
This is a deeply pragmatic, structurally profound way to look at the problem. This concept argues that all of our previous theories are overcomplicating things by assuming time is a separate, external river that the universe sits inside.
Right. We tend to view time as an absolute background clock that has always been ticking, and the universe just happened to show up at a certain hour.
But general relativity tells us that space and time are the exact same fabric, SpaceTime. Time is a physical property of the universe, just like gravity or mass. Therefore, time physically literally began at the exact moment of the Big Bang. The timeline of reality is a closed geometry with a hard, definitive starting point.
Which brings us right back to the South Pole analogy from the beginning.
It does. In this model, asking what came before the Big Bang is not a profound scientific mystery. It's a linguistic illusion. The question itself violates its own premise.
There's nothing to answer.
Right. There is no quantum void. There is no larger overarching foam. There is no previous bouncing universe. The Big Bang is the absolute hard start of the timeline. Asking what triggered it is like standing on the South Pole and asking your guide to walk south. The direction does not exist.
It's the universe looking at us and saying, stop asking. The question makes no sense. It's incredibly clean, but honestly, it's entirely unsatisfying for the human mind.
Very unsatisfying.
We are wired for cause and effect. Telling us there is no before feels like a cop-out, even if it is mathematically true.
The human brain revolts against a causeless effect, which is why the theoretical physics community refuses to stop there.
Right. Because if we can't accept that the question is meaningless, we have to look at the final, perhaps most staggering conceptual framework, the fifth idea, the infinite landscape.
If the previous ideas made you feel small, this one will make you feel microscopic. This concept leans heavily into the mathematics of higher dimensions. Without getting bogged down in the specific academic names of these string-based theories, The core proposal is that at a fundamental microscopic level, the fabric of reality is composed of extra dimensions that are curled up so tightly we can't see them.
Okay, extra dimensions, like beyond our normal 3D space.
Yes, and the way these extra microscopic dimensions fold and curl determines the specific physical laws of the universe. The specific shape of the fold dictates how strong gravity is, how heavy an electron is, and how light behaves.
The shape of the dimension writes the physics rulebook.
Exactly. Now, the math suggests that there are a mind-boggling number of ways these dimensions can fold, trillions upon trillions of possible configurations. And the infinite landscape theory proposes that every single one of those configurations is physically realized as its own separate universe, somewhere in a vast, incomprehensible multiverse.
So it's a purely statistical approach to existence.
Entirely. In this landscape, there is a universe where gravity is 10 times stronger and stars collapse immediately into black holes. There is a universe where electromagnetism doesn't exist, so atoms can never form, leaving a void of dead particles. There are trillions of dead, dark, or chaotic universes operating under completely different physical laws.
And then there's our universe, where the invisible dimensions folded in the exact, perfectly precise way required to allow carbon atoms to form, to allow stars to burn steadily for billions of years, and to allow water to flow.
It answers the question of, why is our universe so perfectly tuned for life?
Yeah.
With a statistical shrug. If you roll a trillion-sided die an infinite number of times, eventually you will get the exact specific number that allows observers to exist. We just happen to live in the winning roll, because if we didn't, we wouldn't be here to ask the question. It's the anthropic principle taken to its absolute extreme.
I am practically dizzy right now. We have covered expanding foams of bubbles, infinitely recycling trampolines of gravity, quantum voids birthing reality out of instability, hard mathematical boundaries, and infinite landscapes of dice roll universes.
It's a lot to take in.
It is an absolute feast of human imagination, but we have to bring this back down to Earth.
Yeah.
Because everything we have just discussed is theoretical math happening on chalkboards and supercomputers. What happens when we stop staring at equations and actually look up at the physical sky?
That is where the story pivots dramatically. Because we do not just rely on math anymore. We have built some of the most complex, sensitive instruments in human history, space-based observatories, capable of capturing the faintest, oldest infrared light in the cosmos. We're actively looking back in time.
And what we are seeing is causing a massive, undeniable crisis in cosmology.
Yes, it is.
Let's talk about the observation crisis, because theoretical debates are fun, but physical data is absolute. And right now, these new, highly advanced space observations are creating massive structural headaches for all the models we just talked about. We are pointing our newest telescopes at the deepest, oldest observable parts of the universe, and we're suddenly finding things that fundamentally should not exist.
The community is calling them impossible galaxies.
Mm-hmm.
And to truly understand why finding a galaxy is suddenly causing a crisis, we need to understand the standard timeline of how structures formed after the Big Bang.
Right, let's walk through the timeline, because things didn't just pop into existence perfectly formed.
Not at all.
Yeah.
Under our standard accepted model of the universe, after the initial expansion, the cosmos was a blindingly hot soup of raw particles. It was chaos. It took hundreds of millions of years for that soup to expand and cool down enough for gravity to slowly, painstakingly begin pulling clouds of hydrogen gas together.
A very slow accumulation process.
Extremely slow. Gravity pulls the gas, it condenses, it ignites the very first primitive stars. Then, over hundreds of millions of more years, gravity pulls those early stars into chaotic, messy, unstructured clumps. These are the infant galaxies. Building a massive, beautifully structured spiral galaxy like our Milky Way, with its distinct arms and central bulge, requires billions of years of smaller galaxies crashing into each other, merging, and slowly settling into a stable rotation.
It's like a cosmic kindergarten. It takes immense amounts of time to grow up.
Precisely. So when we point our newest telescopes to the absolute edge of the observable universe, looking at light that has traveled for over 13 billion years, showing us what the universe looked like when it was only a few 100 million years old, we expect to see those messy little clumps. We expect to see the chaotic infant kindergarten.
But that is explicitly not what the new data is showing us. We are finding fully formed, incredibly massive, perfectly structured, mature galaxies. We are finding spiral shapes with heavy elements.
It is a chronological impossibility under our current models. It's the equivalent of walking into that kindergarten classroom and finding a group of 40-year-old adults in tailored suits sitting at the tiny desks reading the Wall Street Journal.
That is a perfect analogy. The data completely breaks the timeline. These newly spotted galaxies are appearing way too early, and they are far too massive. Based on our understanding of how fast gravity pulls things together after the Big Bang, there simply was not enough physical time in the universe's lifespan for these massive structures to have formed.
And this isn't just one rogue data point. It's a recurring pattern of impossible mass at impossible times. But the headache gets even worse. Because it's not just the impossible early galaxies causing problems. There is also deeply weird, contradictory data regarding where we physically are in the local universe today.
Oh, right. Let's get into the July 2025 observations, because this data suggests something wild about our own galactic neighborhood and how it might be actively lying to us.
Yes, this is the cosmic bubble anomaly. Certain extensive mapping observations from July 2025 suggest that our own galaxy, the Milky Way, along with our immediate local group of galaxies, might actually be sitting inside a massive anomalously empty region of space.
An underdense region, a giant void where there is significantly less matter than the cosmic average.
Exactly, a localized bubble of relative emptiness.
Okay, but if we are in a slightly emptier patch of space, why does that matter? How does our local real estate affect our understanding of the Big Bang?
It matters deeply because it could be fundamentally skewing our primary metric for understanding the history of the universe, the expansion rate. If we are sitting inside an underdense bubble, there is less gravitational pull locally. The regions of space outside our bubble are denser, they have more mass, and therefore stronger gravity.
Wait, so if I'm understanding this right, if the edges of our massive bubble are denser than the inside, the gravity from the edges is pulling matter outward, away from us, faster than the normal cosmic expansion.
You've got it. It is like trying to accurately measure the speed and flow of a massive river while you are trapped spinning inside a localized whirlpool. Your immediate environment is warping your perspective. Your local gravity is pulling things differently than the cosmic average. If we are inside an underdense void, we might be miscalculating the true expansion rate of the universe because our local rulers is bent.
And if our measurements of the expansion rate are fundamentally skewed, then our mathematical attempts to rewind that expansion back to the Big Bang are inherently flawed. We are doing math with a broken ruler.
Exactly. So we are forced to debate the core reality of these anomalies. We have impossible ancient galaxies that shouldn't exist, and we have local empty bubbles breaking our rulers. Are these bizarre findings simply glitches in our brand new instruments? Or are they genuine cracks in our foundational understanding of the cosmos?
That is the multi-billion-dollar question. How does the scientific community handle data that breaks their models?
The first, most rigorously conservative approach is always to assume human or mechanical error. When the physical data drastically contradicts the established model, you check the instruments. You assume a calibration issue. And right now, many researchers are arguing exactly that. They suggest that perhaps there's an unusual amount of cosmic dust bending the light, or that the specific wavelengths captured by the new telescopes are tricking us into thinking these early galaxies are more massive and mature than they actually are.
Basically saying, the universe isn't broken, our glasses are just smudged.
Exactly. And that is a vital scientific process. But what if it isn't a smudge? What if the calibration is perfect, the light is accurate, and the tools are working exactly as designed?
If the tools are right, then the standard model of the universe is wrong, or at least deeply, fundamentally incomplete. If there genuinely wasn't enough time for these massive galaxies to form under our current timeline, it means the timeline we've constructed is cracking.
And if the standard model is cracking, the implications are profound. Every single theoretical idea we discussed in the first half of this deep dive, the expanding overarching foam, the bouncing gravitational waves, the quantum emergence from the void, they are all built on the foundational assumptions of the standard model.
They are built on the timeline that the impossible galaxies are actively tearing apart.
Exactly. If the standard model changes, the theories of the origin must be completely rewritten. It is a profoundly sobering realization. We are spending decades trying to mathematically deduce what happened before the cosmic house was built, and we suddenly get observational data suggesting we might not even fully understand what the house is actually made of.
Which brings us to what I personally think is the most profound, emotional, resonant part of this entire deep dive. We have explored math that actively self-destructs at the edge of time. We have explored brilliant theoretical frameworks that are permanently impossible to test. And we've looked at brand new telescope data that is actively confusing our timeline. So how do scientists actually cope with this impenetrable mystery?
By embracing an incredible, deeply necessary dose of humility. When you synthesize all the sources, all the debates, and all the frantic research papers, the deepest takeaway is actually a philosophical one. Many of the world's most brilliant cosmologists are now openly, publicly admitting a very difficult truth. Humanity may simply never answer the question of what happened before the Big Bang.
And I think for a lot of people, that is deeply frustrating to hear. As humans, we are wired for resolution. We want the answer. We want to flip to the final page of the mystery novel and find out who did it and how.
We crave certainty. But cosmology constantly forces us to confront what philosophers and scientists call the false summit problem.
Explain the false summit.
Anyone who has ever climbed a major mountain has experienced it. You're exhausting yourself, hiking up a steep incline. You look up and you see the sharp peak against the sky. You push yourself to the absolute physical limit to reach it, believing that once you stand on that point, you will have conquered the mountain and will see the entire world below you.
But then you finally crest the edge.
You crest the edge, exhausted, only to realize that what you thought was the peak was just a lower ridge. The actual summit is still miles away, towering infinitely higher than you previously imagined, hidden behind the clouds.
Every time science thinks it has reached the top of the mountain of reality, every time we think we've finally discovered the ultimate foundational answer to where we came from, the clouds part.
We discovered that the stars were other suns, a summit. Then we discovered that the Milky Way wasn't the whole universe, but just one galaxy among billions, another summit. Then we discovered the universe was expanding. Then the cosmic microwave background. Then the quantum fluctuations. Every single time we answer a massive question, the answer itself breeds an exponentially deeper, more profound mystery.
We just keep finding more mountain. But the beautiful thing is, finding a false summit doesn't make scientists turn around and go home. They just keep climbing. The creativity in the face of the unknown is astounding. Just look at this brand new theoretical proposal from June 2026. The literature frames this as a highly speculative, entirely unproven idea, but conceptually it is stunning.
It is a genuinely beautiful hypothesis. This new proposal suggests that we might be looking for answers in the wrong way. It suggests that the universe itself might be actively, physically recording its own history into the very geometric fabric of spacetime, a cosmic memory.
A universe with a built-in hard drive. The idea that the invisible fabric of spacetime isn't just an empty, passive stage where physical events happen, but that the stage itself permanently retains an imprint of the actors who walked across it.
The theory posits that incredibly intense events, massive gravitational shifts, or fundamental quantum state changes at the moment of the Big Bang leave permanent, microscopic, localized deformations in the fabric of space-time itself, like heavy footsteps walking through drying concrete.
So, if this proposal holds any weight, it implies that the universe literally does not forget. The information of the beginning isn't lost behind an impenetrable wall. It is etched into the very room we are sitting in right now.
Exactly. And if we connect this cosmic memory concept to the bigger picture, it intersects brilliantly with several topics we've explored in previous deep dives.
Oh, absolutely. This reminds me instantly of our deep dive on the nature of time. We spent an hour exploring the concept of the block universe, the theory that the past, the present, and the future all exist simultaneously in a rigid four-dimensional block, and our consciousness just moves through it.
Yes. If space-time is actively recording its own history through physical deformations, it acts as a bridge between the human perception of flowing, chronological time, and the physics concept of a static, permanently recorded block of reality. The past isn't gone, it is physically encoded in the geometry of the present.
And it also connects to our deep dive on the many worlds interpretation of quantum mechanics. If every possible quantum outcome creates a branching, separate reality, does the cosmic memory of space-time record all of those branches? Or does the fabric of our specific universe only remember the path we specifically took?
It fundamentally challenges our understanding of shifting realities. If the memory of the absolute before is permanently, invisibly encoded in the fabric of the now, then perhaps the answers to the origin of reality aren't lost behind a singularity wall or wiped clean by a bouncing crunch. Perhaps the exact mechanics of the Big Bang are written everywhere, all around us in a mathematical language we simply have not yet learned how to read.
That is an incredibly hopeful, beautiful way to frame the pursuit of science. Learning to read the invisible language of the universe. But even if we accept that optimistic view, even if we accept that we might one day read the cosmic hard drive, we are still left with the sheer, raw, philosophical shockwaves of the question itself.
And those shockwaves are inescapable. Because no matter what physics model you prefer, no matter what telescope data you analyze, you eventually hit a fundamental logical paradox that the human brain is simply not evolutionarily equipped to handle.
Which brings us to the final act of this journey, the deepest versions of the origin question. Let's grapple with the real philosophical vertigo. Let's talk about causality.
Cause and effect. It is the absolute bedrock of human logic and the foundation of our entire understanding of reality.
Things happen because other things caused them to happen. A glass shatters because it was dropped. A star ignites because gas compressed. Every action has a reaction. Every event has a definitive physical trigger.
But apply that foundational logic to the cosmic origin models we've explored. Look at the bouncing universe, eternally recycling, or the infinite overarching bubble foam, eternally boiling. These are models where the overarching reality genuinely, literally had no beginning. It has simply always existed.
But if reality has always existed, does the concept of causality even mean anything anymore?
That is the paradox. If the universe has just always been here, cycling forever, then there is no first cause. There was no prime trigger. There is simply an infinite, unbroken chain of effects stretching backward into a bottomless eternity.
And I don't care how good you are at math, the human brain cannot process an infinite past. We can handle a really long time. We can imagine 1 trillion years. But an infinite past means that a never-ending amount of time has already happened before this exact second. It is a bottomless well. To me, an eternal universe with no start is infinitely more terrifying than a universe that just popped into existence.
It breaks our causal intuition. Our brains desperately demand a start. We want a first page to the book, but an eternal universe aggressively refuses to give us one.
So let's look at the alternative. Let's reject the infinite past. Let's say reality did have a hard, absolute start. Let's go back to the quantum vacuum emergence, the idea that the universe tunneled into existence from absolute, perfect nothingness. Even if we accept the dense mathematics that nothingness is inherently unstable, what could have possibly triggered that first instability?
If you have a system of absolute zero, a void of pure nothing, and suddenly it violently becomes something, our logical minds scream for a catalyst. What pushed the first domino if there was no finger and no domino and no room for the domino to fall in?
Which briefly brings up one of the wildest theories we covered a few deep dives ago, the simulation hypothesis. The idea that our entire physical reality, from the galaxies down to the quantum particles, is an incredibly advanced digital construct.
Right.
Because if the universe literally sprang from nothing, is it possible that a system from the outside pressed start? Could the Big Bang have just been the sudden, violently energetic boot-up sequence of a localized cosmic server?
While the simulation theory is highly speculative, it is actually just a modern technological metaphor for a very ancient, deeply rooted philosophical concept. The prime mover, the uncaused cause.
The ultimate catalyst that sits outside the rules?
Exactly.
Right.
Whether you call that catalyst a simulation architect at a computer terminal, a divine omnipotent creator, or a spontaneous, localized quantum fluctuation, you are essentially doing the exact same logical maneuver. You are pointing at the inexplicable void of the Big Bang and saying, the trigger came from somewhere outside the physical system.
But doing that doesn't actually solve the problem. It just moves the goalposts.
Precisely. It is the ultimate paradox of existence. Because if you say, okay, a higher dimensional alien architect triggered our universe, then your brain immediately demands to know, where did the architect's universe come from?
And if you say, well, the laws of quantum instability triggered the Big Bang, you are forced to ask, where did the abstract laws of quantum mechanics come from? Who established the math? You can push the question back as many layers as you want through simulations, gods, or quantum multiverses, but you always, inevitably, end up back at the exact same cliff edge. You always end up staring into the void.
Which brings everything. The impossible galaxies, the supercomputer simulations, the expanding bubbles, and the broken rulers. Back to the absolute core concept of nothing. The total terrifying absence of reality. If our universe arose from a state of pure nothingness, because nothingness is inherently mathematically unstable, where did that specific brand of nothing come from?
How can a state of pure nothing have mathematical rules dictating its instability? If it has rules, it isn't nothing.
I can hear the vertigo in your voice.
It's the false summit. We climb and we climb and we climb. We build massive supercomputers to simulate the unsimulatable. We launch $10 billion space telescopes to stare at the edge of time. We write equations that span massive chalkboards. We stretch the human mind to its absolute physical limits. And we just end up standing on the edge of the exact same ultimate cliff our ancestors stood on when they looked at the night sky.
And perhaps that is exactly where we are supposed to be, staring out over the edge, deeply humbled, recognizing the profound limits of our own perception. Because if we connect every single piece of evidence we've explored today, the broken math of the singularity, the endless recycling bounces, the impossible early galaxies breaking our timeline, and the unstable boiling void of the quantum vacuum, it leaves us with one final fundamental question to consider.
What is it?
If the universe truly came from nothing, does nothing actually exist?
Wow, just let that sit there for a second. That is the kind of question that physically rewires your brain. And to you listening to this right now, I really hope you let that final thought bounce around your mind today as you go about your life. Because feeling incredibly small in the face of a universe that is vastly stranger, vastly older, and vastly more complex than we ever could have imagined, it is a wonderful thing. It is a gift. It reminds us that there is always more mountain to climb and more mysteries to uncover. And sometimes looking into the void and openly admitting that we do not know and perhaps fundamentally cannot know is the most honest and the most fiercely scientific position we can possibly take. Thank you for joining us on this massive, mind-bending deep dive. Let the mystery linger in your head today. We'll see you next time.